I hear you.
Good morning. We start our session. We start our session about laser interaction with matters, and the first speaker will be from China. Can you hear us?
Yes.
Okay. So please, your presentation will connect about the perovskite rays and the analysis, as I understand. Please, you have 20 minutes. So, okay.
Okay, yeah. Thanks, Professor Pop, and for the invitation. My name is Xunhan from Zhejiang University, Hangzhou Global Scientific and Technology Innovation Center. My topic is controlled fabrication of the metal halide perovskite arrays for the large-scale opto electronic integration. So my report is divided into three parts. And metal halide perovskite is a classic of the materials with a specific structures of ABI3 type, and this structure gives perovskite very uh, unique properties, and can be obtained through the low temperature and solution process methods. And perovskite has demonstrated very important applications in the lights and lasers and photodetectors such as perovskite photodetectors has very wide applications in the various fields, including the health monitoring and optical communications, spectrometers, and fingerprint scanners, and the artificial and the electronic eyes with bionic human eyes functions, and color reconstruction devices. And for the perovskite photodetectors have the wide applications in the various fields, including the health monitoring, optical communications, and the uh, single device. And we know that about 8% of the information that human perceives from the outside comes from the vision. And the human eyes is a very precise optical system that can achieve wide field of view and multicolor and large depths of the field imaging. All kinds of the optical system have the basic curvature of the image field, and the curved surface structure of the retina is more consistent with imaging field, so which make it inherently suitable for the correcting abbreviations. So it can bring the higher imaging qualities and simplify simple optical structures. And so, but for the product materials, their low temperature growth method and can achieve the flexible devices and expected to achieve breakthroughs in the low noise and high performance of the flexible and curved images, and to
Excuse
achieve
me,
the high quality.
Professor.
Sorry.
Sorry, we just see only your first slide with the topic of your presentation. Is it okay?
So you can't hear my voice. Is that right?
Yeah, here it says six slide. Okay.
Yes.
Don't
Yes,
forget
I'm talking about the
to.
aspects.
Okay. Thank you.
So it is right. Yes. Currently it's slide 6. Okay. Okay, let's keep going. So to achieve the high quality image performance of the perovskite device, the first step is to fabricate the perovskite material arrays. And compared with the continuous film, the perovskite arrays has many special applications, but the perovskite materials decompose in polar solvents and make them incompatibility with the traditional microfabrication process, and therefore the current therefore the current let me therefore the current method is the current perovskite arrays it is very this one. Yeah. It's very small scale and in the low resolution. Our work is to bridge the perovskite materials and traditional lithography process to achieve the both large scale and high resolution perovskite materials and devices arrays. And then, as I mentioned, one of the important advantages of the perovskite material that it can be fabricated in the solution method. So then we saw that we could separate the precursors solutions before the crystallization, and we
I'm
use
really
our
sorry.
method.
I'm really sorry, Professor Xan Han. We see the same slide. It's a number 6. It's a motivation of your work. It's okay.
No, it's not right. Currently, it's
Okay.
slide 8.
Don't
Probably,
forget to list your slides because we see only because I think you forget about it. Anyway, please.
okay, so our method is to separate the separate the precursors and using the surface functionalization. And in this way, during the coating, only the hydrophilic areas will return the precursor solutions, and there is no solutions in the hydrophobic areas. So then we use the two-step method for the crystallization. After crystallization, we can receive the perovskite arrays, and you can see that we can through this method we can fabricate the large scale arrays, and each pixel's position and shapes and can be precisely controlled. So, and based on the Bow's array method, we first deposit we try to make the large scale flexible photodetector arrays, and the first step is we try to develop the deposits the electrode arrays on the flexible PT substrate, and then we use the mentioned the method to prepare the perovskite arrays. And you can see after the device here we make a 10 by 10 array, and it is flexible, and has very electric mechanical stability. And next, we characterize the photo response performance of the device, and the device response can cover the whole response of the visible light bands, and it demonstrates very excellent photo response properties, including the high on-off ratio, detectivity, and the stability. This device can also show very good uniformity, so
Sorry,
we
again.
can
Sorry, Professor Xang Han. We just see previous slide. I think you need to move to another one. No?
so which slide you are seeing?
Okay.
That's 10 is so probably I can't do the full screen. Maybe it has a delay. So I'm sorry about that. So I will use this the small screen
Yes,
here.
because we have a delay between your pronunciation and your slides. So we can stop here, and please tell us when you will move to the next slide, and if it will be a mistake, I will tell you, okay?
Okay, so okay. So let me see. So we using this array device, we can achieve the real-time tracking of the light spots and the real-time imaging of the light intensity. And so how to improve the stability of the perovskites? And so we know that the all in organic perovskite arrays demonstrate improved stability. So we saw that whether our method can apply to the all in inorganic perovskite arrays. And for this one, the film coverage of this array is very poor because the low solubility in the solvent. And here we did the here we did some modification, and first is added the vacuum, and we added the vacuum conditions and to improve the coverage. And in this method, and it can nucleate quickly and increasing the nucleation density and prepare the dense films. You can see here, and the materials can growing on a large scale on the ultra thin parylene substrates and can completely peel off from substrate using the electrochemical methods. And then we did the ultra thin arrays, and which is fabricated on the ultra thin parylene substrate with 1.1 micrometer thick. And then we did the electrode arrays and the perovskite arrays, and then do the encapsulation. Also, we use ultra thin parylene C film as a encapsulation film. The total after the fabrication, the total thickness is only 2.4 micron, and it is lightweight and it can flow on the water, and it can form the conformal contact on the curved surface. And you can see we attached the device to a finger, and you can see the fingerprints very clearly. And next, and we check the performance of the device, and you can see the scalability is improved. And after 6 weeks, there's no new XRD peaks, and there is a decay of the photo current is very slow. Is very small, and it also can endure the stretchable the stretchability. And when then attach the ultra thin devices on the on Hermes port, and it can imagine the light distribution. And then we apply these materials to the lead-free perovskites. And for example, the copper-based perovskite materials, through adjusting the vacuum degree and controlling the nucleation and the growth pattern, we can prepare the large scale and the copper-based perovskite arrays. And using this method, and we fabricate the flexible solar blind for the data arrays, and it can also demonstrate very high stability and high photo response properties, and it can realize very weak light sensing with an intensity of 6.1 nanovolts of the solar blind light. And then it can be used for the flame detection and warning, because the flexibility of the device, and we can attach it on the semi-sphere the spots, and with 8 arms, and with 8 arms for each arm it has 5 points, so it can detect the flames and at the different locations, and it can achieve the single point detection and the multi-point detection. And compared with the polycrystalline materials, the single crystals and have a various performance improvement. We try to give the growth the single crystal arrays using this concept to separate the precursors. And there is more control over the crystal nucleation. The first is use another using another hydrophobic glass to give it is another to give it a z direction conformant, and using the anti-solvent crystallization method to improve the crystal qualities. And using this from here, we can using this method we can achieve the large scale crystal rays of the 10 centimeter by 10 centimeters, and we can do different patterns of the crystal provide crystals, and this those including the pixel positions and macro plates, the width and the it's the the crystal width and the crystal thickness, and furthermore furthermore we can grow the we can grow the crystals on different substrates. For example, here we can grow it on the S2 and K2 and the K2 substrates, and it can realize a special growth, and so we can control the in-plane rotations. For example, the crystals grow on the S2 substrate, and the rotation degrees with distributed in a very narrow range. It is it is very minus 2 to plus 2 degrees, and for Westbound glass is the rotation the rotation of the crystal is distributed randomly, and we also can change the precursors and to control the composition of the perovskite crystal rays. And here we can achieve the prepared array from the green emitting to the blue emitting rays. And the device, the crystals also demonstrate very high crystal qualities, and it can serve as a high quality WGM mode laser macrocavity, and it's showing very small threshold for the lasing, and high the quality the Q factor, and the multi-mode, the single mode to the multi-mode lasing properties, and it can be controlled by through changing the thickness and the width of the device of the crystals. And we also demonstrate uh, the uh, the photo detector integration based on the crystal arrays, and it can show high response rate of the and high specific detectivity and fast response. And previously, I talked about the four types of the photo detectors, but all these four types devices, and based on the photoconductor structures, and but it means for this type of devices, the electrode occupied very high space space ratios of the substrate, and for to integrate uh, to to achieve high resolution, and we should use the photodiode structures. And for this device, a problem is the fabrication of the top electrode, because the incompatibility with the microfabrication device, and so currently it is using the shadow mask. It is hard for alignment while the pixel is small. Here we deposit. Here
Sorry,
we develop
Professor.
a
Sorry, I'm really sorry, Professor Hanuk-san, but we have not. We should move to conclusions because it's not a lot of time. Okay.
Okay. So
Okay.
yes,
Please
yes.
go
Here,
to
here we
the conclusions. Yes.
okay. So this is the last part. So we using this method and fabricate a very high resolution devices here, and it is a universal fabrication strategies, and it is suitable for different perovskite and different organic semiconductors. And the next is conclusion, and we using the surface functionalization concept and fabricated different large-scale arrays of perovskites, and we can fabricate the single crystal perovskite arrays and high resolution devices. And this is thanks for the support from my collaborators and colleagues and the fundings. Thank you.
Thank you very much, Professor Han-Ksung. We have any question? No question? I have a lot of questions. First of all, I would like to ask what is the stability of your perovskite materials? I mean, is it survive under sun radiation and it's stable, it doesn't degrade?
The stability depends on the types of the perovskites. For the hybrid perovskites, and the stability is not very good. And we usually do the encapsulation to improve it. And for the all inorganic and the perovskite single crystal arrays, and it demonstrates very good stability. And for example, it can so it can continuous working for for about 7 hours, and for the all inorganic devices, and it can store in the air for 6 weeks. So there is no change on of its structure and the performance.
Okay, and the next question what I have, what's the rate of your productivity to prepare these films and perovskite materials? It's you need a lot because you use photolithography. Sometimes I think it will be quite hard to do it. I mean, it's a industrial production, or it's just samples. Just for experimental.
So our method using the photolithography to do the to prepare the perovskite arrays, and for the in the industry, and I think it's issue using the main challenging is to how to achieve the large scale and high resolution fabrication of the perovskite arrays, because it usually decompose in the solvent in the organic solvents, and usually the fabrication of the perovskites is as the last step of the device fabrication.
Yeah, I see. Yes, it's a really nice presentation, but we haven't the time anymore, and I would like to contact with you. Actually, at the morning I sent you a mail, but you didn't answer me. But please answer me because it's for me it's really interesting. Thank you very much for your attention, and we should to thank our presenter. Thank you.
Okay, thank you. Bye.
Bye. And our next speaker also will be online. It's Gavril Voloshin from St. Petersburg. And his presentation will be about resonance coherent population trapping in cells. Are you here? Can you hear us, Professor Gavril Alexandrovich? Can you hear us?
Yes, I hear.
Okay. Good morning. Please, you have 15 minutes. So let's start.
Well, can you see my presentation?
Yes, we can see your presentation.
Perfect. And first of all, I would like to thank organizing committee for the opportunity to make the presentation here about our work dedicated to coherent population trapping detected by the Ramsey method in the alkali atoms. And at first, I would like to remind you of the essence of this phenomenon. This phenomenon is observed when three-level atomic system interact with two frequency laser radiation. Difference between the tuning of these radiations, interaction by the lambda scheme like this, and difference between detunings we will call two-photon detuning, determines the coherent population trapping state. When actually we have two quantum system with two channels of excitation that can destructively interference with each other, and we can see it like deep in the dependence of population of level excitation level to two-photon detuning, and this deep means that system don't interact with external field. It's trapping on the ground state, and width of this resonance can made much smaller than the width of the natural absorption line, and this fact let us find application for CPT phenomenon for different practical area, such as quantum frequency standards. And recently is the so-called Ramsey scheme. Ramsey scheme has become widespread, and the essence of this scheme is actually in pulse feeding of external field. First, long pump impulse pulse transfers the system to the stationary coherent population trapping state. Then we have long dark pulse, and then the next short rate pulse, the read system in the population trapping state. And as a result, we have a number of resonance that have that narrower than CPT resonance. And the width of such resonances is determined only by time of dark pulse, and can be smaller than the main CPT resonance, much more. And researchers often use the simply three-level model for describing of theoretical describing of these resonances, but widely known that the additional levels in the system of atomic levels strong change the Ramsey resonances by form and by shift for frequency, and that's why aim of this work to construct the mathematical model of interaction of two frequency laser radiation with full magnetical levels of atomic system for the D1 line of alkali atoms. And we have the statement of the problem, like gas cell with alkali atoms and buffer gas actually interact with two frequency laser radiation. The medium is optically thin. We have a non-zero temperature of our medium, and we will neglect the collective scattering effects. Well, mathematical model of this description is based on the density matrix method, which satisfy in Wigner representation by translational degree of atoms to this quantum kinetic equation that when we can add the relaxation term and collision term. Hamiltonian of atom we can write in the standard form, like Hamiltonian of a free atom and Hamiltonian of an interaction with the field in dipole approximation. Here we can see full system for elements of density matrix that we integrate by velocity, and it is population of ground state, population of excited state, low frequency coherence, and Zeeman coherence. But optical coherence we can't get for reductively density matrix element by integration for velocity, and that's why we get it from this equation, from itself equation, and put it on the first system, and as a result we have the system of integral differential equations that we can solve numerically. The calculation results were compared with the experiment. As a result, we observe qualitative agreement of the results. The better when dark pulse we have more short. Let's discuss the other result for atom of rubidium, and here we can see the dependence of the resonance amplitude of the on the magnetic field. We can see non-monotonic dependence here of the amplitude of the magnetic field, and here we can see just three resonance for different lambda scheme on the magnetic transition with magnetic moment -1, 1, 1, -1, and double lambda scheme on the 0, 0 transition. And dashed curves here is continuous resonance detected by continuous radiation. And this resonance we can get for Lin-Paralin configuration, so-called. And this resonance we get for Lin-Paralin configurations. And here we can see that central resonance, there is no central resonance because transition double lambda scheme on 0-0 transition here two lambda scheme in this transition interact interference destructively, actually. How it was observed in this work. Here we can see the dependence of resonance amplitude on magnetic field, and we can see the non-monotonic dependence of amplitude. We can have such minimum of this dependence of amplitude for different values of magnetic field, and we can explain it by the possibility of destructive interference of different lambda scheme, and we get some relation for this interference, and from this relation get the value of magnetic field when resonances has minimum amplitude for different dark pulse.
I'm really sorry, Professor Voloshin, but you have just 1 or 2 minutes, and you should move to conclusions because we don't have any more time. We need a time for discussion, and please go to conclusions. I'm sorry.
Okay. We also analyzed the dependence of resonances on ellipticity of external, and we can hear the non-monotonic dependence here also with maximum for circular polarization, sigma plus, sigma minus, and also we also dependence of light shift of resonances by the temperature and ellipticity was analyzed, and here we can see the brief conclusions of my speech. Thank you for your attention.
Okay, let's thank to our speaker. Thank you very much for your interesting talk. We have any question? Nobody have not a question? Has not a question? No? Okay, I have a question about have you tried the method of Ramsay-Bordet interferometry? What is compare with your method, just with the Ramsay method?
Our method is actually Ramsay method.
Yes, but it's another method. It's a Ramsay-Bordet method. It's a bit different.
Sorry, I just not hear about this method.
Really? Okay. Anyway, we can speak with you by mail or by WhatsApp because we connect with you today, tomorrow, or at morning. So, any question? Maybe somebody decided to ask? No? Okay. So, let's thank our speaker again. And we move to the next our speaker. It's Professor Yuri Chivel from Saint-Étienne, France, and he will be present finally on site. So please, you have 20 minutes and you can go here.
Good morning, dear friends.
Please use microphone.
Yes. Okay.
Something doesn't work?
There is a known method and the devices that implement it for the obtaining of powders by evaporation. The target will a laser beam and subsequent condensation of the vapor of the target material in the gas flow. As the process is carried out in the evaporation mode and the process productivity does not exceed 100 grams per hour at energy cost of 40 watt-hour per gram. There are numerous works on the preparation of nanoparticles in a liquid by laser ablation, but their effectiveness is extremely low. The most productive at present are the methods of gas and plasma atomization. During gas atomization, supersonic gas jets spray a jet of molten metal. The range of sizes of the obtained particles is about 3,200 microns, but the very high cost of melting a large mass of metals and the power and efficiency of the process is about 4 kilowatts hour kilogram. Plasma atomization seems to be technology providing the best yield of quality powders with the range of 3,200 microns. The plasma atomization family of the processes remains very inefficient energetically. For example, a typical plasma atomizer could use 3 plasma torches set at a power of 45
You are currently the only person in this conference.
kilowatts each and a preheat source to atomize a titanium wire at a range of 5 kilograms per hour. They represent more. In addition, these processes do not allow obtaining nano-sized particles. It would thus be desirable to provide a novel apparatus and process for producing spherical powders in a wide range of particle sizes, from nano to micron sizes at large industrial scale. The main reason for the low efficiency of industrial powder production processes is the low concentration of the energy flow. During plasma atomization, the diameter of the sprayed wire is 3 millimeters and the diameter of the plasma flow is 20 millimeters. With gas atomization, a large amounts of metal is melted inefficiently. A new approach has been developed to the process of obtaining powders using highly concentrated laser energy sources. A laser is a special optical scheme using conical laser beams. The developed optical scheme is shown in figure 1. In this system, the wire is introduced in the focal region of the single conical beams on the focal region of a system of several laser beams arranged around the perimeter. The end of the wire is heated to melting and sprayed with a supersonic jet of inert gas. It is atomized. The moving source that For moving source, the temperature distribution over the surface in a moving coordinate system has been such form. There are a simple solution for the fast and the slow motion of the heating spot. The calculation of the process of heating a steel wire with diameter of 2 millimeters is carried out. The diameter of the focusing spot of the wire is 2 millimeters. The calculation performed showed that at the intensity of 10⁵ power watt centimeter, complete melting of the wire takes place at the wire feeding speed about 4 centimeters per second. And the productivity of the process is determined by the speed of the melting wave. The productivity of the process is up to 5 kilograms per hour at a laser radiation power of 10 kilowatts. In such an atomization process, as in the case of gas and plasma atomization, the size of the particles obtained is in the range of 30–100 micrometers. At the same time, the problem of obtaining nanosized powders with high industrial productivity is extremely urgent. To obtain nanopowders, condensation of particles from the vapor phase is used. The vapor phase is obtained by ablation of the material with a laser, an electric arc, etc., followed by condensation in the continuous gas flow. But the so-called gas phase condensation, as shown in a number of works, this method is well controlled and allows one to obtain nanoparticles in the range from individual molecules to 1 micrometers. But the production of nanoparticles on an industrial scale has not been achieved, since the scale of devices is extremely small. Our approach is based on the use of unique properties of conical laser beams and the continuous optical discharge. This makes it possible to increase the scale of device at a high specific power of energy input. Evaporated object in the form of a system of wires with a diameter of about 1 millimeter is introduced in the focal region of the conical laser beams from the laser system or a system of several beams, conically focused by conical mirrors. Part of the laser radiation evaporates the wire continuously fed into the least area. The remaining part of the laser radiation flux is focused in a small spot and generates a continuous optical discharge with dimensions of in the order of the some centimeters in the various vapors and the surrounded gas. To maintain the discharge in the optical discharge with a temperature of about 20,000 kilowatts, a power of several kilowatts is consumed. The wires are continuously fed into the optical discharge plasma, continuously evaporates by the laser radiation and heated by the plasma. The discharge is poured with an inert gas flow. The structure of the discharge in the gas flow is shown in figure 4. The process of heating and evaporation of the thin wire will, when it is introduced into the plasma of the optical discharge, will simultaneously exposure to laser radiation is considered. The limiting speed of the introduction of vira into the region of evaporation and plasma formation will be determined by the speed of the evaporation wave in the vira. The evaporation material is blown through the plasma of the optical discharge by the inert gas flow, and at the discharge outlet begins to condense in the gas flow at the highest degrees of supersaturation, forming nanoparticles. We should dwell on the issue of maintaining the optical discharge. The absorption of the discharge plasma is proportional to the square of the wavelength of the laser radiation. Therefore, the discharge is well supported by CO2 laser radiation, but the efficiency of the CO2 laser is only 10% for a large system size and cost. The study carried out in VOC showed that the problem can be solved by placing an optical discharge in the laser cavity. Due to gigantic number of passages of laser radiation through the discharge in the cavity, radiation of any wavelength can be used to maintain it. Diode lasers with high efficiency are the most promising in our optical scheme. The optical discharge is placed in the resonators of the L1 laser or in the resonators of several diode lasers placed in pairs with an external cavity. Productivity of the power production processes depending on the power density of laser radiation, and we can see on the figure 4. The large transverse dimension and the large length of the continuous optical discharge in the transverse gas flow create opportunity to the implementation for another variant of the method for obtaining micro and nanoparticles with high productivity. A jet of irregular raw particles with a large cross-section about 1 centimeter with a particle density of up to 100 centimeters and the speed of 1 meter per second is introduced into a continuous optical discharge in a transverse gas flow. In such a concentration of particles of millimeter size, the transmission coefficient of laser radiation will be about 0.5, and at the laser system power of 10 kilowatts, the optical discharge is maintained. Heating and evaporation of particles occurs due to direct laser radiation in the caustic of the conical beams, and a heating by optical discharge plasma, by radiation and convective heat. Calculations show that at path length of 4 centimeters, complete evaporation of particles up to 0.4 millimeters in size take place in the optical discharge. Larger particles will melt and become spherical. At the exit from the optical discharge, we will obtain spherical micro and nanoparticles with a process productivity of several kilograms per hour.
I'm really sorry,
Okay.
but we
Okay.
should move to conclusions. Sorry.
Okay. The laser evaporation of solids followed by vapor condensation is perspective method of nanopowder production. When a conical beam of laser radiation is introduced into a dense powder jet, almost complete absorption of radiation is ensured. On this basis, a method and devices have been developed for obtaining nanopowder by laser ablation of a powder jet from particles of micron size. Theoretically and experimentally, this method was verified. The experiment for nanopowder production was created in the form of evaporation condensation chamber. The powders obtained in the experiments are conglomerates with a size of
I'm really
100.
sorry, Professor Civeli.
Okay.
We should move to conclusion because we don't have any
Okay.
time. Okay?
Okay.
Please.
New methods and apparatus for production spherical nanopowders using laser radiation in a wide range of particle size from nano to 100 microns at large industrial scales are developed. Thank you for your attention.
So we can thank our speaker. Thank you very much for a nice presentation. And if we have any question, nobody have any question? Okay, I have a question. It's a simple question. Maybe I have missed. What kind of gases you used in your experimental setup?
We use nitrogen or argon.
Nitrogen and argon. And why you use it these gases?
It is inert gas.
Okay, as I understood, you did a different kind of metal particles on a titanium. What kind of metals also you produce?
Steel and titanium.
Steel what?
Steel and titanium.
Steel and titanium. Okay, thank you. Any question? No question? Okay, let's thank our speaker again. And we will move to the next presentation that will be presented by Maria Grigorieva from Lebedev Physical Institute, and her topic will be Maria will tell us about her topic. I forgot. I'm really sorry about the investigation of a short pulses laser ablation of porous silicon with molecular dynamics simulation. So we have a theoretical section. So let's start. Okay, we will wait. No problem.
Okay. Good day, dear colleagues. My name is Maria Grigorieva. First of all, I would like to thank the program committee to the opportunity to present our work. Today, I will talk about the investigation of the short pulse laser ablation of porous silicon targets with molecular dynamic simulation. Okay. It's well known that silicon nanoparticles are non-toxic, biocompatible, and biodegradable materials. That's why they are very promising for different biomedical applications, such as cancer therapy, drug delivery, including nuclear nanomedicine, as a synthesizer for different types of therapy, bioimaging, and so on. And how we can to form the silicon nanoparticles from porous films. The films themselves are produced by electrochemical etching, and after that we can use mechanochemical or ultrasonic ringing or for nanoparticles production, or we can use a pulse laser ablation of such films. In our work, we simulate the laser ablation of porous targets with different porosity and pore size under the radiation with several wavelengths and various fluencies. For molecular dynamic simulation, we use the open soft lamps, and also we write in some additional programs for generation of pore structure and temperature profile creating using Python. The modeling was carried out in an area of 10 per 10 per 100 elementary cells. The arrangement of atoms is assumed to be the same as in single crystalline silicon with the lattice constants of 5.43 angstrom and diamond-like lattice. As interaction potential, we use a 3-particle Tertsov potential. And in our model, the absorption was simulated by an instantaneous change in the temperature of atoms with certain coordinates, and also the absorption model proposed full absorbance of incident fluence, so the fluence can be considered as absorbed fluence. In this case, the temperature profiles is expressed in following way. You can see here. And the pore radius is generating using long normal distribution, and the density and linear absorption coefficients are assumed to be proportional 1 minus P, whereas P is the volume porosity, which is a ratio between volume of pores and the total volume of materials. Okay, here you can see some examples of our simulation. On the video, on the left video, please turn on the video. Yes, there is an interaction of laser pulses with 300 nanometers wavelengths and fluence 0.1 with a single crystalline target. The atoms in crystalline lattice are yellow, colored yellow, and no-coordinate atoms are colored in blue. And we consider silicon atom as ablated if the distance above the substance surface is more than 1 nanometers. It's above orange line on figure 1. And yes, here on this slide, there are a few more simulations. The left pictures is the same as the previous slide, and the right video is ablation of porous silicon target with porosity is about 60% and pore size 2.5 nanometers with the radiation of 300 nanometers and fluence is 0.01 joule by square centimeter. Okay, let's analyze the obtained results. This figure shows dependence of the number of ablated atoms on target porosity for pore size of 1.2 nanometer and irradiation with wavelength 300 nanometer and 600 nanometers. First of all, I should say that main and obvious results consist in significant difference with pulse laser fluences, which need to ablate the same amount of materials with strongly and slightly absorbed light. The latter case is characterized by nearly monotonic decrease of number of ablated atoms versus the porosity target in the figure 2C. At the same time, at the ablation with ultraviolet radiation with small fluences, the number of ablation atoms for porous targets can increase with increase the porosity. But at highest fluence, the highest ablation rate corresponds the bulk silicon. And that we can see the presence of pore leads to decrease of ablation rate, which may be due to the hindering escape of atoms from the ablated structures due to the presence of pore walls. Nevertheless, relatively small fluences can cause ablation of porous target and has not effect for single silicon crystalline targets. Okay. The modeling of the dependence of the ablation rate on the pulse fluence was carried out in order to evaluate the ablation threshold. We assumed that the ablation threshold is a minimal value of fluence which leads to the ablation of at least n atoms. Because the atoms number fluences near the threshold. The threshold is calculated as a mean of fluences with correspond n between 1 and 5. In our investigation, we didn't find significant difference at ablation threshold for bulk silicon and low porous silicon with irradiation of 100 nanometers. It's picture 4b. It's about 2 joule per square centimeter, and its decrease for 0.7 for porosity is 0.8. The ablation with ultraviolet light result in more significant dependence of laser ablation threshold on porosity. And the picture 4a. And it should be noted that the effect is more pronounced for the smaller pore size. And such drop in the ablation threshold can change the laser ablation efficiency in nanofabrication processes of porous silicon targets. And to verify our hypothesis of the decrease in ablation threshold, we carried out some experiment. We use a porous target with porosities about 60 and 80%, and the irradiation was carried out by linear scanning of the sample with a laser beam for 3 seconds, and the wavelength was 1030 nanometers, and pulse direction was 270 femtosecond. And the ablation threshold in our experiment, the ablation threshold was considered to be the last value of the laser radiation energy density at which ablation craters represent. And on this slide you can see the results of our experiment. In the table, blue values correspond the absence of craters, and the red value corresponds to the presence of craters. And thus, the experimental ablation threshold for bulk silicon was about 0.75% joule per square centimeter, and for porous silicon target was about 0.35 joule per square centimeter. And I want to say that these results are in good agreement with another experimental results of another scientific group from Moscow State University, and also with good agreement with our simulation results. In conclusion, I'd like to say that modeling of the ablation process by molecular dynamic methods made it possible to estimate a decrease in the laser ablation threshold for silicon using a nanostructured porous substrate. An increase of the porosity to 80% leads to 1.5 to 3 times decrease of the ablation threshold compared to the bulk silicon, and a decrease of pore size from 2.5 to 1.2 nanometers leads to a stronger ablation threshold drop, and the effect is stronger for the ultraviolet radiation. The decreases example was a large contribution of the surface and the weakening of the average bonding energy in the substrates. And the reduction of the ablation threshold can be of particular importance in the laser ablation synthesis of nanoparticles. Thank you for your attention.
Okay, we should thank our speaker for her nice presentation. Thank you very much, Maria. If we have any question, yes, please. I'm really sorry, Naila Limovic. You need to speak English.
What is shown here? I don't understand. Where is crater? What is this strange?
It's craters for...
Or it is edge of the crater, or what? Where crater is?
No craters. It will be linear skin, and there's some part of the linear.
Why? It is not a focal point. Was not a circle.
No.
How?
Oh, with scanning linear, we move.
Scanning.
Yes, scanning the line, and it is a part of this line. It's maybe not. I should not say the crater, so maybe line.
And for ultraviolet, your threshold is so small. Only.
It's not ultraviolet radiation.
No. Before it was.
Yeah.
So large difference between ultraviolet and
Violet and with yes.
Nanometers. Yeah?
Yeah, 300 nanometers
So
and 600 nanometers.
Yes.
That's
For A, ablation threshold is only 4 millijoule, while
yes.
why it is so small? 4 millijoule.
Because they are highly absorbed.
Okay, but it is, you show it is just 10 nanometer skin layer. Before it was shown the absorption depth. It was something like 10, alpha 0, 10
10 per 6.
6
Six.
power. This means that it is 10 nanometer depth. So it is usual as is metal, but we know it's so small.
Maybe this for porous materials, and which the porosity is.
But okay, I have an additional question that in the experimental you have usually normal fluids, 1 joule per centimeter square, but here you have just 0.002 joules per square centimeters, and this is our question, Ismail. Okay, we can discuss later, and you will answer us. Thank you. We should move to the next speaker and next presentation. Let's thank our speaker again. And the next presentation will present by Dr. Evgeny Zavitzeyev from General Physics Institute, and his topic will be connect with laser cavitation and liquid hydrocarbons. So you have 15 minutes, please, Evgeny. You have 15 minutes for all. Okay?
Thank you. This work was done by our group in General Physics Institute. Optical breakdown in liquids is a complex process which includes a number of fast dynamic components, from the formation of a dense non-equilibrium plasma to cavitation. In solutions, suspensions, and even pure liquids, the chemically pure synthesis of various nanomaterials and nanocomposites can be realized at laser intensity exceeding about 10 to 13 watts per square centimeter. Laser cavitation and pulse repetition rates can affect the beam focusing and thus suppress the photochemical reaction. The presented experiments are stimulated by a study of laser synthesis of linear carbon chains in liquid hydrocarbons. We investigate regimes of cavitation induced by a near-infrared femtosecond laser, picosecond laser, in ethanol and N-hexane. Here is our simple experimental setup. We used 1064 nanometer laser with duration of 10 picoseconds and maximum repetition rate 500 kilohertz and pulse energy up to 80 microjoules. And we used ethanol and hexane and microscope to visualize the cavitation. So, can you see the bubbles in the focus? I hope. If at small repetition rates, we can create small bubbles in the focus that have size of several micrometers, and they fastly disappear due to the condensation of vapor. And the pulse repetition rate is 50 Hertz. And if we increase the pulse repetition rate 100 times, we can see multiple bubbles appear in the focus. The size of the bubbles is 10 micrometers, and the bubbles move fast from the focal area in random direction. And if we increase the pulse repetition rate 100 times more, we see nothing in the focus, usually. But sometimes we see something like this, appearing of a bubble in the focus that shifts relatively slowly towards the source of the light, and it grows in size, and apparently the laser light traps the bubble. And if we shift the camera towards tracing this bubble, we can see it continue its movement for some time, then stops to shift and grows in size up to 2,000 micrometers in diameter. So we call it super bubble because of its size. And when the super bubble disappears from its place, the new one replaces it. The super bubble was observed at every pulse energy above the cavitation threshold, and pulse repetition rates that are needed to form a super bubble are higher for higher laser energies. It can be because faster bubbles driven by stronger jets are harder to trap. And if we turn off the light of our microscopic system, we can see, you can see the picture on the right, on the left and top, laser plasma, a radiation of plasma induced in the laser focus. And we can use its brightness as a criterion of energy that reached the focus. So when the cavitation is low, the brightness of plasma is proportional to the pulse repetition rate. When we have a strong multiple cavitation, it affects the light penetration into the focus, and we have a decrease in plasma brightness. But when we have super bubble, we can see no plasma at all. So it trapped in the prefocal area super bubble distorts the Gaussian beam to such extent that it practically stops to focus and produce the laser-induced plasma. And and in the superbubble affects not only the plasma formation but also the efficiency of photochemical reaction. So again, large cavitation, multiple cavitation can decrease the efficiency of photochemical reaction, but the superbubble practically stops it. And we propose the next possible mechanism of bubble trapping and superbubble formation. So there are two peculiarities of the superbubble. It can grow and so get new molecules and energy far from the laser focus, and it has some force acting on it that stabilizes it in space, in particular prevents it from floating up. It is possible that the superbubble obtains energy from single photon absorption in the liquid, which is non-zero in this wavelength. But wherever it gets the energy, it has molecules that constantly evaporate into it from the liquid, since it grows in size. And the bubble position is shifted with respect to the laser axis, so the evaporation must be more intense in the lower part of the bubble. This should provide a reaction force on the bubble boundary which can compensate the buoyant force. And the same force can drive the superbubble away from the laser focus at the early stage of its formation. This effect is opposite to balloon rocketing. Everybody did it in childhood, and somewhat related to photophoresis. So let me conclude my talk. Laser cavitation induced in ethanol and N-hexane by 1064 nanometer 10 picosecond laser has been studied at pulse repetition rates up to 500 kilohertz and energies up to 80 microjoules. For each pulse energy above the threshold for cavitation and high enough repetition rates, the light traps single cavitation bubble or a few bubbles that shifts from the focus towards the laser source, grows in size up to 200 micrometers in diameter, and blocks the beam focusing in the laser-induced photochemical reaction. The pulse repetition rates that are needed to trap the bubble are higher for higher pulse energies. A possible explanation of the bubble trapping mechanism is proposed. Thank you.
Okay, thank you very much, Dr. Zavidzeyev. We thanked our speaker. We have any question? Okay, please.
Well, thank you very much. Very interesting observations, especially for us because we did something similar, but our bubble was near the surface. So okay, so very interesting, and it will be interesting to discuss maybe later about details.
If you have some ideas about the mechanism, it will be very
but it's
precious.
Just optical breakdown. And we see diffraction. It is small, order of wavelength, so it's significant diffraction of light around it.
Okay, we'll discuss.
Okay, thank you.
Yes, about diffraction, it's a really very good question, Professor Nagaev. And also maybe I have missed what's the size of your bubble?
200 micrometers at the largest, largest size. So
Yeah, it's really nice because I have read the abstract about your work with Professor Tarasenko. So yes, we really can discuss about this in a coffee break. So let's thank our speaker again. And we have any question more? Professor Konov? No? Okay, so let's move to the next, our last presentation on this session. It will be done from India by Dr. Susheta Janieta. And please, you can start your talk. Can you hear us?
Thank you.
Okay. You have a technical problem with your microphone because we have a lot of sounds. Yes, yes. You should. No, no, no. It's a. No, no, no. You still have. Oh. No. No, it's a bad sound. Please check your microphone clearly. Now we cannot hear you at all. No. No at all. We cannot hear you, Susheta. I'm sorry. No. Sancheta, we cannot hear you at all. Please send a message to technical support chat. Okay, we will wait you. Okay. We should wait around 2 minutes. Yes, we can see you, but we cannot hear you. Yes. Thank you, Daria. Sorry, maybe извините, все слышали объявление, то, что если кто-то хочет опубликоваться в физиксового феномена в этом году, то можете написать мне письмо или Климентову, или на нашу вот почту, которая вот у нас указана, и всем все организуют. Это очень... Yes. Now we can hear you, Sashita. Yes, we can hear you now.
Thank you. Okay. Just I'm going to share my PPT, ma'am, now. Can I do? Can I start?
Yes, you can start. Yes, yes, please.
Okay, ma'am. Just 1 minute, PPT. Now you are like to hear me as well as see my PPT on screen, ma'am?
Yes, we can see your presentation and hear you very well. Thank you. So let's start.
Thank
please.
you and sorry. Yes, sorry for the disturbance.
It's okay. It's okay. Relax and just present your nice talk.
Sure.
Okay.
Sure. Thank you, ma'am. First of all, ma'am, I would like to many my best wishes, congratulations for this organizing this international conference on the ALT 2023, and my best wishes to Samara University and all the partners for organizing team. And thank you very much for inviting me to present my presentation on such a great and wonderful platform. I've had an interaction with you all, innovative persons. And now today I would like to present my presentation on fabrication of innovative grating structures using laser technology for solar cells applications. And I'm presenting my CSIR NPL, that is National Physical Lab in India, and Jindal Saw Limited in India. Now, as the topic of my presentation is fabrication of innovative grating structures using laser technology for solar cell applications. First of all, there are different methods to increase the efficiency in photovoltaics device, mainly solar cells. We need to use some advanced concepts of for light trapping. What happens when there is some loss of incident radiation, so we didn't able to get the efficiency of the device. So there are two ways. Conventionally, the texturing method is used for the light trapping. Recently, diffraction gratings is used, and that is based on the diffractive element. This is the diffraction of incident light into large diffraction angle. This is the main important point that is responsible for the efficiency of our device. And there are different shapes of grating. First of all, these are rectangular, pillar, and these are blaze shape gratings, as well as there are many different shapes which will be possible. And more importantly, that all the theory studies presently now on numerical or simulation based are available. Now only a few of the experimental studies are available. Nowadays it is a very interesting, exciting area of researchers, topic for research for the researchers. First of all, I would like to introduce what is diffraction optical gratings. Diffraction optical gratings, basically it is important in the field of optical application systems like optical communication, optical information, and optical sensing systems. LEDs and LEDs widely used as light sources in these systems that give their compactness, low driving current, and high speed modulation. Basically, the light source transfers to optical fibers, then the output beam, the emitting from the source, has far field radiation angles that need an external lens such as collimating lens or a focusing lens. But these lenses are so bulky, so it is difficult to compact, collimated or focus light for these micro-optical applications. So these type of optical elements, diffraction gratings, has overcome such problems, and given a great deal of research has been performed. Because of their high uniformity, lightweight, as well as these are used in imaging purposes applications also. What I have done in my research is that I fabricate some of the grating structures. I fabricated in Samara National University. I visited also Samara National Research University as a senior there and work under with Professor Shvedlana Konina and Pavelia in the department, and there did I fabricated some laser grating structures, that is with circular laser based system, and then I deposited silicon thin films for the solar cell applications in India. This fabrication methodology used to realize gratings, and they are used by I fabricate silicon thin film by a technique, and the silicon layers are deposited, and then this we go for analysis, and we found very many of the interesting and are published in paper with Professor Konina and Pavelia. Now, early that incorporation of photonic enhanced light draping was performed initially by James Key, but now it shows the enhancement of 4n square, where n is the refractive index of the material. Or of course, for optics purpose, refractive index is mandatory. Several groups photonic crystals with gratings to enhance the light trapping capabilities of solar cells. The novelty of our design lies in a fundamental approach to designing solar cells. Both work as a single as well as multi-junction solar cell, that is of different band gap, so that it reflects what we consider the transmission characteristics of the device. So we design accordingly so that it reflects shorter wavelengths back into the first cell and transmits longer wavelengths to the lower energy cells. So we combined this, we proposed a model for the solar cell. This is the function of grating. What is the difference between the grating and the interference or diffraction simple phenomena? This is like phenomena, and this is the diffraction grating, where light incident on this, it passes through the structure. On another light on this, it passes through the structure. This is a simple phenomenon. Let's makes an angle theta, it makes an angle. So light diffraction, when the light comes on this, it goes through under optical path length increases with the diffraction. For smaller gratings, the diffraction angle is increased, light is diffracted at higher. When light comes from here, it goes here. It goes from far, it goes from out to far. So this leads an increased optical path length in the structure. So this is due to this property, it attracts or excites our research in this direction. So we variate the period size of the gratings, fabricated groove height and shape. So I used the sputtering system for sputtering. First film deposited using sputtering on a substrate, and then we go for laser lighting system, circular laser lighting system in Samara National Research University, and via wet and chemical etching we got this type of structure at different period of 2 micrometer and 4 micrometer. Obviously we can go beyond this of the nanometer range also with other electron beam lithography technique. This is a system of our system, and these are the samples, these are the machines equipment, this is the plasma etching setup, and this is our fabricated grating structures. Then we study the morphological studies, yani FESEM on this grating structure. We found such good images, and definitely I character is the same there in the Samara National Aerospace University, no, Samara National Research University, sorry. And this is it's clearly shown this is the grating of period 4 micrometer, and here is this mentions the height. This is the height mentioned given, and this is the period. Same, this is the period of 2 micrometer clearly identified in the image. Then I studied the intensity distribution at different of wavelength for covering the range from visible, covering full visible range, 4 micrometer as well as 2 micrometer. Then I study the interference results, and it clearly shows how it reflects back the light. This is the very wonderful, great image we got at the period of 4 micrometer. At the period 2 micrometer, it is not image is clearly visible. And calculate the roughness of the sample via the surface profiler. Then what I did, after the fabrication of these structures and have the good results, I go for the deposition of their silicon thin films on top of this for the solar cell application, solar cell technology, and via PCVD system in India. And there I deposited silicon thin films with a deposition rate of this angstrom per second, and then I characterize the film via XRD and SEM again. These are the so sharp crystalline peaks are appear at our this for at this film 4 nanometer. At this it's only 1. The more is this film the crystalline nature. Then I fabricate the SEM image of only film structures. This is on the without grating structures, SEM studies. Only silicon structure is observed, grains are observed. Then on gratings, I have deposited gratings, I deposited silicon films. These are the structures. And it is clearly mentioned how the good images in this, and these are well published in a paper, and these are the clearly visible, these crystalline grains are embedded with the grating structures. This is the two-dimensional images, taking the consider with the JAS FECM advanced scanning electron microscopy, and also I take the cross-sectional view also to have the exact idea of the film structures. This is the very beautiful film images. I got it with the scanning electron microscopy. And more details are published in my research paper. You can have there. I can share with you if you require, if you want to work in this direction. I am ready to cooperate, have a collaboration, and also would like very interested to work more on this with the simulation as well as experimental. Then what I observed with this finally that I observed enhancement is the absorption spectra, that is mainly for required for the efficiency of the device. More is the absorption, more is the device efficient. So this is our quartz substrate, and we have studied silicon with grating parameter 2 micrometer and 4 micrometer. It is clearly visible that this grating with 2 micrometer we found 95% absorption in this, and nearly 60% absorption with this, and this is without grating. So this is quite interesting. And this also we observe for 2 and 4 micrometer, and in this we found this in the lower range covering the visible range we find good absorption in these films. So this is why, this is due to the grating structures, the wavelength is light is low in the range, much longer than the period or height. So that's the reason that incident light can easily penetrate through the grating without interacting or further recombination or any loss. So incident waves might change their direction to neighboring unit cell. That further increases the constructive interference and effective light rating. So the reason is the multiple total internal reflections might occur in this. So this increase the path length and increase the absorption. This is I proposed the solar cell structure with gratings, with discussion with Professor Pavelia, Professor Kunina. Wonderful opportunity, wonderful experience. This is the concept basically showing the multi-junction. This is my future plan to fabricate some multi-junction solar cell with short wavelengths being reflected to first cells being transmitted to lower energy cells. What are the advantages? Mainly that they are to be low cost, high effective, alternate way of reflection, large scale of applications. They have leads to scattering and higher order diffraction. This results in increased absorption in thin film solar cell. And grating on the top, more advantages. If we can apply the grating structures on top as well as on the bottom of the device. On the top of the absorbent layer, it reduces the reflection loss. Now, finally, I can conclude with the time, as the time limit is low. I can discuss more. I can give my email ID. You can take it from anyone, or would like to have more discussions and more interaction. wavelength, improving short circuit characteristics and at the same time transmitting long. The gratings are effective approach to light trapping in silicon thin film solar cells. Nowadays, I am also working in terahertz field. So this is my list of publications. I have published more than nearly 25 publications. Thank you very much.
Okay, thank you very much, Professor Juneja. We should thank our speaker for her nice talk. We should to thank.
Thank you. May I have some questions? I am ready to answer. If
Yes,
you have any.
and we have any question? No questions? Kularai?
Okay, thank you very much.
I'm sorry. I have a question. I would like to know details about your Polaroid coordinate laser writer. What it was an experimental setup about when you did your gratings.
Yes. Ma'am, I fabricated these grating structures in the same yours university, my university, Samara National Research University. Previously, it was Samara State Aerospace University there, with a circular laser writing system in the main building. And there it is very well. I can share my PPT with the complete setup details of the system with you. If you want more details, I can share.
Susheta, it will be very, very nice if you will send me, because it's very, very interesting how you did it, and it's really nice technology.
Sure.
Yeah, okay. You can contact me, or you can send a mail to our contact center, and they will resend me.
Sure.
Okay? Yeah, thank you very much. It was a really nice talk. So, thank you. We need to thank our speaker again. So, thank you very much, Professor Juneja. Yes, have a nice day. And our session...
I share my...
sorry?
Ma'am, sorry. For you, I share my email ID in the chat box here. You can see and contact me anytime.
Okay, yes. And Dari will send me. Thank you very much. Thank you very much, Professor Juneja. Sorry. And yeah. So, we should to close our session. It was last presentation, and the next session will start at 11:30, and his chair will be Professor Kucherik. He is here, and I'm really thank everybody who came this morning and survived. Anyway, so see you. Thank you. And also we have a plenary session at 1 o'clock here. Okay? So, thank you.
Пока не видно. А мы имеем там соединение, нет? У нас должен был человек еще один подсоединиться. Аксен Гендлер из Китая.
Нет, это последний Аксен.
А кто еще?
Первый Чу.
Это такого у меня не написано ничего. У меня Лукашенко, Самохин.
А, это у Кати он достался.
Да. Там индианка была тоже онлайн.
Да.
Индианка. Все.
С Катей.
Оксен Гендлер. Сидел, ждал такого монитора. А потом должен был серьезно, ты что там ждешь? Давай рассказывай, да? Okay. Let's start our final session about laser matter interaction, and we have 3 offline speaker and 1 more in online. And our first speaker is Stanislav Lukashenko from Lebedev Physical Institute of Moscow. Okay, let's start. And where's our another phone? It's no problem.
Hello, dear colleagues, and thank a lot to organizers. Today I will discuss the post-processing of nanoparticle synthesis and with the spotlight on laser-assisted fragmentation method. Yes, and the usage of molecular dynamics method, we focus on silicon nanoparticles that are significantly targeted in biomedicine. Nanoparticles in biomedicine have seen exponential growth over 2 decades, and they have applications in photoimaging, biosensing, and targeted drug delivery. Silicon nanoparticles are attractive via their biocompatibility, efficient surface chemistry modification properties, biodegradability, high porosity, and bioimaging properties. And we, you know, a lot of big variety of methods of creating, of synthesizing nanoparticles, and most of them under the development in nowadays. The most promising method is pulsed laser ablation in liquids method. Why? Because of this versatility, cost effectiveness. The nanoparticles have no radicals and chemical reagents, so non-toxic, low chemical impurities, well controllable sizes, and are in a good colloidal condition in liquid solutions. But this method it depends and based on some numerical parameters, such as duration of pulse, energy density, and particular wavelength of the laser. We tried to reveal, and there are such some theories that describe the mechanisms of its process, but there is no clear understanding of these processes. There are several theories, like Coulomb explosions, phase explosions, relay instabilities, and decay of molten metal droplets, and so on. So we try to make a molecular dynamic simulation of this process, and our system is incorporated with Stirlinger-Weber potential for silicon, material for nanoparticles, embedded atom method for water molecules, and modified Lennard-Jones potential that combine the van der Waals forces between silicon and oxygen, and the fact that silicon was wettable in water, so it's adhesion part of potential. We have 384 processors, and they are divided like this. So MD parameters, you can see here the MD parameters. So we have the cube of water, 100, 100, 100 nanometers in 3 directions. The diameters of nanoparticles, the degree of porosity, so the potentials, incident influences, durations. We have periodic boundary conditions. The process of absorption is described by Berenson thermostat method. So the energy of laser is distributed to the atoms via scaling the velocities and corresponding to the Gaussian profile of the laser pulse. It should be our system aiming to describe mechanical properties mostly of water, of the liquid, and thermophysical properties of the water. Actually, generally speaking, we can't describe the absorption like this. So nanoparticles is not the bulk system. So because of the depth of penetration is much larger than the sizes of nanoparticles. So we should solve the Maxwell system and calculate the cross-section of the nanoparticles. So because the nanoparticle could absorb in resonance way, could scatter the light, and so on. And and in our calculation, we accord that the cross-section of absorption is equal, the effectiveness of absorption is equal 1. Actually, to apply the results of our research, you should, or we should, make multiply to the proportional coefficients to real, to true cross-section of the particles. For example, if it's 10 nanometers silicon in water, we should calculate the absorption cross-section. So if it's 0.05, we should multiply by the factor of 20 our fragmentation thresholds. The first tries of our simulations we can't observe the fragmented secondary nanoparticles, and the first first idea was that there are no enough shock wave of neighboring explosions of neighboring particles, so the almost spherically bubble are collapsed, so very symmetry, and molecules of water can't go faster than the silicon, so the silicon slips in one drop occasionally, all times. It's failed, fragmentation failed. And we tried to assume the fact that neighbors are closer, or they are collapsed more efficiently. So we assume this with different fluences to different nanoparticles in one computational cell, and the fragmentation was done well. So, and it's clear to see that the asymmetric of the bubbles are observed, and there is some dependence on the fluence of the dependence of the sizes of secondary nanoparticles on the fluence of the incident fluence. Monolithic porous nanoparticle does not fragmentate, and so the 20 nanometers, 30 nanometers at this incident fluent does not fragmentate. So we suppose that 0.015 joules per squared centimeters is close to the fragmentation threshold of these nanoparticles, 10 nanometers, silicon in water. Let's look closer to the contours, and link the atomistic pictures with plots of contours, temperature and pressure contours. So the accumulation of the stress is relaxed. So the maximum of the accumulation is about 11,000 kelvins, and it was observed by a third picosecond, and above the critical value of 500 kelvins, 5,000 kelvins, and the pressure is about 7 gigapascals. Was inside the particle. So this accumulated stress was relaxed, and the shock wave start moving outward, and refraction wave starting move inward the particle. And at the same time was the nanoparticle was evaporating. Then this atoms was like bumping the border with the water and cooling, and become liquid. Liquid security, like liquid nucleation, is observed, and so this is a shock wave, like blue one, light blue. And at the third 30 picoseconds, the evaporation of water started. Then the shock wave bump in the surrounding media that
You are currently the only person in this conference
that have the pressure above the shock wave, and the water starts moving inward, and the cooling speeding up, and then it distinguish secondary particles, and so we have like well fragmented secondary particles. So here from 10 nanometers it become 2 to 5 nanometers. So, and at 100 picoseconds, the final collapsing the bubble and increasing the pressure, increasing the temperature. Then at 225, it's okay. It's like enough solid, and water media have no significant pressure gradients and temperature. So it's briefly scratch a fragmentation process. So we have like two conclusions. Average size of the secondary particles is a function of the applied fluence. The process of the fragmentation is influenced by the interfering shock waves propagating from neighboring fragmenting nanoparticles. And this system could be improved and with no reflection boundary conditions. So we could implement absorption according to the field theory, but our approximation is acceptable with recalculating the thresholds. So thank you for your attention.
Okay, thanks, speaker. And some questions? Oh, Sergey.
Hello, thank you for the interesting insight to this problem of fragmentation. If I understand it right, you didn't take account of electrical charges. So definitely it's not charge explosion, but it exists.
Yes.
And it is strong.
Yes. I think that we should make some criteria when it's stronger, when it's weaker. So if the duration of pulse is above the time, the character time of electron-phonon interaction, so in our system is about 1 picosecond for these nanoparticles. And if we make the pulse around 1 picosecond, so we could avoid this, as I see.
No, you cannot.
No.
Because you have immediately the electron emission, and it does not depend on electron-phonon relaxation. It's happening from the surface, and surface is very large in this case. It is observed in electron emission spectroscopy, for example. So you have immediately polarization. You have immediately a charge accumulation in the particle. That's really what you mean. So if we have time, electron can relax, but they do not have time to relax. So they go outside. They go outside, not thermalized. So it affects only the temperature of the particle, because energy is taken away. Okay, so you do not take it into account. Yeah, okay. And the second question, so your main mechanism is a shock wave. So the fragmentation is driven by the shock wave, right?
Yes, like asymmetry of shock wave, primarily nanoparticle.
Yeah. Are there any data which stands for this idea? Any experimental data comparison?
No, at now time it's no experimental like.
Okay, so what do you predict with nanoparticles of initially different size? What's happening if we vary the size of nanoparticles? So it's happening, what we obtain finally?
We can predict that, so it will be almost the same, but with the meaning, with understanding the wavelength and the absorption property of particular particle.
So there is no strong dependence, right?
Yeah. Yes,
okay. Okay.
We think so.
Thank you very much. Thank you.
Okay, thank you for your interesting question. Another question? Okay. Only one, please.
Could you finally compare your dependence of average size of the fragmented particles from fluence with experimental data? Because such data exist. And how is corresponding between?
Such data somehow exist. We can, but we need also the concentration that we have, because the distance between particles is very, yes, very important. Yes, so we tried to find. There is no like good experimental results to compare. So it needs to do. Yes.
Okay, let's thank the speaker again. Thank you, Stanislav. Okay. Okay, and our next speaker is Alexander Samoshkin from Prokhorov General Physics Institute.
First of all, good morning to everybody in this room, especially after the very good evening yesterday. And taking this into account, I'll try to be as brief as it possible. Oh, let's start. In our research, we consider behavior of aluminum film heated with 30 picosecond laser pulses up to stress, pressure, recoil values which is higher than possible critical pressure. But nevertheless, in this case, some subcritical events can happen below the surface because in some subsurface layer, the pressure is not so high. We use the well-known molecular dynamics and two-temperature combined with two-temperature approach, as it shown in the next slide. Too much. Where is the... No. Some slides is omitted for unknown reason. It's not me. And on this slide, you can see the pressure behavior on two depths under the irradiated surface at 200 nanometers and 400 nanometers. This signal is typical for thermoelastic or thermo-optical mechanism, but there is small peaks, pressure peaks, on this curve. You can clearly see it. At first glance, it resembles vaporization peak in nanosecond regime, but that is not so, as it will be clear later. This signal evaluate as follows. With growing fluences. And in addition to this peak pressure, another peak appears, delayed peaks, in about 150 picosecond, which it clearly can be interpreted as cavitation effect or bubble collapse, at least 2 times were said about in this room. But the first peak is not vaporization peak. And this is another delayed peak. and it is due to melting front movement, as it can be seen from another representation, former representation of the result. This form. This is temperature. It's a usual representation form. Black line is melting boundary moving inwards. It's density, and then in this picture you can possibly not show any specular feature which can be attributed to pressure signal, but at pressure behavior, it is clear that this orange line, you can see, it is clearly due to melt front movement. So it is not vaporization pressure. Vaporization pressure in this situation is quite small compared with the whole thermoacoustic signal, and the signal due to melt front movement. This is the first main conclusion of this research. And the second, this is evolution with growing intensity or fluences. And the second, delayed peaks, appears under the irradiated surface in the liquid state. You can see such line which goes to 250 picoseconds. This is a pressure pulse. And it originates in a liquid state. And sometimes you can hear it as it reflects from boundary, melting boundary. Maybe you see V sign reflection. And yet another form presentation of the result is as follows. You can see that the scale, space scale is quite another as compared with previous slides. You see vaporization process and heat expansion of the target and occurrence of cavities which results in spallation of some part of materials. But in addition to this obvious, prominent, manifested, as you can say, effect, yet another effect can be seen, which demonstrates originating and then collapsing of another bubble, which is the origin of the second delay pulse. Such effect in the metal target in picosecond regimes is not obvious beforehand, while as it is not new. Our main goal of this investigation is finally to find manifestation of critical parameters in non-equilibrium laser ablation processes. This is a fundamental problem which is not yet resolved. Thank you. Conclusion.
Okay, thank you. It's very interesting presentation, but some question? Oh, okay, thank you. Hey.
Thank you very much. Very beautiful presentation, simulation. We also did something similar for 70 picosecond, and I want to emphasize for all of us that there are larger difference between 1 picosecond, half picosecond, and 50 picosecond pulses. They are significantly different. And I want to ask you, at the last picture, where was the level? Zero level was initial level of the target, because it is expand too much. Вот предпоследнюю. Вот, да, вот это. Вот 0 это zero is это вот
It's initial zero.
То есть она 30 nanometers expand too much. And also I want to ask you, it will be better if you plot the intensity of a pulse together with you, because you begin your pulse 60 picosecond before the maximum.
Maximum of the intensity is located on 60
picosecond. Yes, so too late and not obvious.
It's all events after the pulse. It's
yes,
after
but
the pulse.
Okay, but if you show
Vaporization quickly diminishes after the pulse. You can see.
Yes. It just some methodical. First of all, if you put picture before, yeah. Well, for example, here you see zero is 60 picosecond before the maximum. So the maximum is at with 60.
60.
But
when the melting curve appears.
Yes.
Approximately.
Yes, but how it is at 50 picoseconds arrive. So it is, the maximum is later. Okay, I just want, было бы лучше, если бы тут вот этот нарисовали. Вот где у него максимум, как он там нарастает, как бывает.
Но главный, the main conclusion from this picture is that the events is after the pulse. After the
pulse, yes. But how late after? How late?
More than 100 picoseconds.
Because you have to pass to 200 nanometer and 400 nanometer to pass with velocity of sound.
No. You can.
But in any case, thank you very much for your report. It is indeed interesting and useful paper. Thank you.
О, ты что? Ты что ж такое? Никак. Че же он так перескакивает-то?
Вы нажимаете просто мимо нужной кнопки.
А он сам бежит. Я не нажимаю. Here you can see that the collapse appears about 200 picoseconds at the surface. At the surface. Begins, да. Collapse occurs. Collapse occurs.
Okay, we understand. Thank you. Let's thank speaker. Thank you again. And our next talk from Kirill Zhilin. Where is he? Okay.
Good afternoon, dear colleagues. Thank you for possibility to introduce our experience. My name is Kirill Zhilin. I'm commercial director of company LLS. So I want to introduce our products and some interesting application that will be, I think, interesting for you. So company Northlace located in St. Petersburg, and our main goal is to create new interesting devices for scientific application, for technology, and so on. So our team works with lasers more than 10 years, and now we have about 30 people in our team. It's only researchers and scientific. There is no guys that are working with financial or something else. It's our products. Today we create laser sources and amplifiers with different parameters, with different form factors, and especially our specialization is fiber lasers and hybrid lasers. Also, we produce solid-state lasers. Components and special laser systems for special applications, first of all. One of our products is single-mode continuous wave fiber laser. Yeah, you can tell that many companies all over the world already produce the same systems, but in our situation right now it's really difficult to use such systems because of sanctions, and also we can it's difficult to organize servers for such systems if the production facility of this device is located in foreign countries. So now we already have 2 kilowatt fiber lasers, and we're discussing more powerful sources with our customers. Another good devices, it's picosecond fiber lasers. So we can do classical picosecond for 0.6 nanometers. Also we can do green or ultraviolet laser sources, and parameters will depends. First of all, it's energy parameters, but for different application we can choose what's the best solution. Also, we produce high frequency hybrid laser sources. We're speaking about frequency more than 10 kilohertz up to few megahertz. One of our products is diode pump quantrons. We can use it for creating high power lasers. We can use it for created lasers with big energy parameters. I will show you later one of interesting project where we use such quantrons. When we create these laser systems, we choosing non-standard applications. We're interested in special applications. For example, this laser system was created to control irradiation stability of electronic components, and we use for different customers, for different methodics. We used in one situation picosecond laser. In another situation, we used solid-state laser. So our customer creates methods of controlling. So they use laser radiation to work with solid to work with Getcher structures and check parameters after these interactions. Another system that was created with our laser source was a system for scribing of semiconductor structures. So we also used, in this application, we used solid-state laser, and we got good parameters of for create these structures. It was high speed system. Here's a photo of the working system. Also for some applications we create system or some that includes not only laser sources but also some optics. For some devices we use standard optics from our partners. For special application we create these optics by ourselves. So one of application of such devices deals with medicine. So we produce system that makes a special line on ampoules that helps to the doctor, to medicine brothers and sisters easy open these ampoules. Interesting system, and it's already worked on customer's facility. So another project deals with treatment of special wafers. We can create in different layers these wafers. We remove some material and create different layers. Now in Russia we can't find some interesting and useful applications. For example, we don't have right now equipment for aviation. It's really interesting technology, and it's called laser so laser hardening, yeah. But in this technology, we use high energy in pulse, and we are trying to change the surface with help of collapsing waves. So inside this system we use about 10 joules pulses in nanosecond pulse duration. So we create really high power and high peak power in these devices. This laser was created by our team, and it's one of application, but it's really interesting systems for special applications. And the last one system that I want to describe for you, it's a system that used ultra-fast laser sources. So we sometimes we need to create small holes for drilling, for example, and production lines that wants to use this technology. They asking to create minimum zone, a minimum area of changing material inside the object. For example, you can see the picture on the right corner. So diameter of these holes about 250 microns, and the area that can be changed while we drill in this hole is about 5 up to 7 microns, and it's really difficult requirement. Now we are working with our partners to find a way how we can create such holes with so difficult requirements. Thank you for your attention.
Very interesting laser devices. Okay. First question from Vitaly Konov.
In some technological applications, it is very interesting to use only few picoseconds, not 50, not 100, but say 5 or 10 picoseconds. Is it possible with your devices?
Right now we have only devices with 50 picosecond, but we are working on this question, and for one of application we need 300 femtosecond.
It's another story. I mean few picoseconds, few.
I will check and give you feedback.
Okay, thank you. Another question? And yeah, during the holes.
But in this case, you can avoid losses. Otherwise, you have great losses of energy. Your system is not efficient.
Yes.
When you're speaking about last point about the holes, on which material you drill these holes? Because if it's not metal, it's not so big problem to have 5-7 micrometers heat affected area.
It's not the sheet metal, it's metal from technology, from liquid technology. And the second point, it's high, it's steels that we use inside engines, in airplane engines, and it's not standard steels.
It's not composites, it's metals.
No, it's metal, yeah, it's metal. Yeah. It's metal.
It's possible to speak about.
Okay.
Okay. One more.
Thank you for your presentation. We know your company. Could you possibly say, is it in principle possible to make a hybrid system which uses final amplifiers of active multimode fibers? They exist in principle, yeah.
I am not a researcher of these systems, so it's difficult for me to answer your question. But it's really interesting question.
Yeah, thank you, and hope to collaboration.
Okay. Some question again? No? Okay, let's speak and thank again. Thank you, Kirill. It's a very interesting question. And our next presentation by online from Boris Oxengendler. Boris, are you here? На Бориса ничего. We don't hear you, Boris, and don't see where you are. Okay. Hello, Boris.
Похож на того актера.
Okay, can you start now your presentation?
Начнете? Уже готово, да? Да. Все. Добрый день, коллеги. Привет вам из Узбекистана. Я очень рад, что вы мне предоставили возможность выступить. Спасибо большое. Спасибо. Значит, я буду говорить по-русски, потому что, в общем, мне будет легче мыслить, перестраиваясь. Простите. Тему доклада вы видите. В общем, это процессы деградации Solid State Electronics, но с точки зрения модерн физических концепций. Ну, нажимайте. Опа. Оно не нажимается. Сейчас, простите. Не идет. У нас? Ага. Вот, спасибо. Значит, очень краткий, малюсенький эпиграф, потому что именно он страшно характерен для той науки, которую сейчас буду представлять. Значит, Пуанкаре сказал, вот там написано, что исключительно важные как раз скачки в науке, скачки смысла еще более важны, чем накопление результатов. И для иллюстрации вот придуман вот такой зиккурат, есть горизонтальное накопление, есть скачки. Вот в науке, которую я представляю, вот это скачки исключительно важны, а их было очень много за 150 лет, как эта наука родилась. Значит, дальше. Вторая часть, которая исключительно важна, из-за такого обилия концепций, и как дальше будет видно фактора воздействия колоссального, есть очень большой искус экспериментаторов после эксперимента сразу давать механизмы. Сплошь и рядом в диссертациях, а на самом деле должны быть на модели. Вот то, что как вот великий экспериментатор и блестящий теоретик поступал со своими экспериментами без моделей, вы видите слово одно «gentle». Теперь дальше. Вот, значит, у меня альма-матер – это Копичник. Назад. Значит, и вот Петр Леонидович Капица говорил иногда удивительные вещи. В частности, вот вы видите, он выходил на сцену и говорил так, задумавшись немножко. Когда у меня что-то не получается, то я иду в зоопарк. А там Бог уже все сделал, только гляди. Что это означает? Это означает, что в нашей науке колоссальное переплетение живого и неживого. Дальше будет это видно. Дальше. Итак, значит, что же я хочу рассказать? Я рассказать о той области хочу, достаточно новой, там, где с точки зрения переплетения радиационной физики, радиационной химии, радиационной биологии удается сделать трактовку и предсказать и протрактовать массу новых типа экспериментальных результатов в области деградации. Дальше. Итак, очень коротко о радиации, чтобы было ясно, с чем мы имеем дело. Коротко. Она вообще огромная наука. Видите, вот методология умещается в 4 позиции. Ну, во-первых, типы радиации, их довольно много, и свет, и нейтроны, и все, что хотите. И свойства какие. Радиация имеет вот следующие степени свободы. Энергия ее, интенсивность, доза, когерентность, поляризация и хиральность, что вышло вообще чуть ли не на первый план в настоящее время. Любые радиационные эффекты можно разделить в какой-то степени на следующие компоненты. Первое. Малые шкалы и большие шкалы. Малые – радиационное дефектообразование, радиационно стимулированная диффузия и радиационно стимулированные химические реакции. А большие – это дислокационное перемещение и перемещение границ. Все под действием радиации. Теперь о каналах передачи энергии от радиации веществу. Несмотря на все огромное разнообразие вот этих радиационных методов и факторов, и типов, оказывается, все можно уместить всего лишь в 5 каналов передачи. Упругое рассеяние, просто удары смещения, выделение тепла, конечно, ионизация. И теперь, значит, упругие волны и ударные, разница между которыми, что в упругих волнах передача энергии идет со скоростью звука, а в ударных больше скорости звука. И, наконец, вот это очень важно, что весь прогресс с высоты птичьего полета, можно сказать так, прогресс нашей области радиационной физики связан с новыми объектами, новым типом радиации, и, в-третье, с новыми концепциями. Вот эта троечка управляет всем прогрессом. Дальше. Значит, очень коротко. Чем руководствуются в таком избытке информации экспериментаторы и теоретики? Замечательный американец и замечательный русский человек, но в Узбекистане жил он. Вот Стародубцев. Они придумали разбиение всего радиационного эффекта на стадии: физическую, физико-химическую, химическую, потом уже превращение в макроэффект, и это все подвергается кинетическому анализу. Вот такому. Значит, в новых вариантах вместо простых уравнений типа химии, где оперирует она средними значениями, вся химия оперировала средними значениями. Оказывается, теперь на первый план вылезают вероятности приобретения того или другого количества компонентов в химических реакциях. Вот это равенство. Оно не укладывается в прежние представления. Дальше. Ну а теперь о комплексити, вот об этом, значит, подходе совершенно последнем, но тоже очень кратко, а потом будут уже иллюстрации на примерах. Будьте добры. Значит, сначала давайте познакомимся с гениальным человеком. Он самый сильный человек в области теории твердого тела. До сих пор живет, слава богу, Андерсон. Вот его позиция. Он в городе Санта-Фе была конференция, он выступил со своим меморандумом. 1977 год. Видите, это нечто, комплекс это нечто больше, чем сумма. Просто обязательно должно появиться новое качество. Теперь, чтобы было новое качество, оно действительно заслужить слово нового, оно, оказывается, должно иметь нечто у родителей должно быть. Во-первых, у прародителей должно быть нелинейное взаимодействие между друг другом, и сами их структуры должны быть достаточно сложны. И, конечно, условия, при которых будет это все протекать, должно быть неравновесное. Вот. Ну, и тогда все это дело, рождение нового, приобрело специальное название, удосужилось. Emergence. Рождение нового, принципиально нового, которого качества не было в прародителях. Дальше. Итак, значит, из каких фундаментальных наук черпал свои кусочки по кусочкам и сложилась концепция комплексити, сложность. Из математики, вот ее создатели этих кусочков, из химии, вот создатели, дальше из биологии создатели, из физики, вот создатели. Понятно, что если по кусочку складывать умно, гениально умно, то получается нечто новое на уровне корней, не на уровне наверху ветвей, на уровне корней. Получается совершенно новая вещь, которая комплексити. Вот эта комплексити, ее обкатывали очень многих уже с 1977 года, и, наконец, она докатилась и до радиационной физики твердого тела в начале 21 века. В основном в нашей ташкентской команде. Дальше. Итак, значит, что такое комплексити? Во-первых, словарь. Какие термины вы увидите, если заинтересуетесь? Нелинейность, неравновесность, нестабильность, флюктуация, бифуркация, диссипативные структуры, фракталы. Самоорганизация, динамический хаос, самоорганизованная критичность. Это последний крик моды. Самоорганизованная критичность. Новое, рожденное вот в таких муках. Философия такая, не редукционизм, который шел от древних греков, а наоборот, снизу вверх, харизм, чтобы не потерять середку. Теперь дальше. АБЦ, то есть лего модели для комплексити, из которых назад. Все проскочило. Дальше. А вот, значит, для комплексити. Неравновесный автокатализ, Пригожин. Дальше. Уникальная чувствительность к начальным условиям, Лоренц, математик. И наш Синай, российский, тогда он был СССР. Теперь следующий Бак, он сделал, значит, нечто такое, которое комбинирует сложность, совместность с локальными флуктуациями. Вот это вот. И, например, и последнее, это Вимер, аж 48 год, как поднимается информация снизу вверх, сжимаясь во всех живых, а теперь уже и неживых приборах, неживых структурах. Дальше. И вот давайте взгляните на великих людей, которым мы обязаны современным уровнем науки в сложных системах. Пуанкаре, Рене Том, значит, Мандельброд, изобретатель фракталов, и Фейгенбаум, изобретатель особого подхода, значит, отображений. Вот это четверка, математическая часть. Дальше. И вот теперь я познакомлю вас с этими четырьмя АБЦ, то есть Лего. Итак, а формул нету. Улетели формулы. Ну, значит, я расскажу. Итак, первое – это следующее. Обязательно должна быть химия, в которой в левой части и в правой части есть одни и те же элементы, типа x плюс 2y, стрелка, 3y. И тогда, оказывается, если в случае еще это будет неравновесность, тогда мы имеем в этих реакциях конечных понижение энтропии. Уникальная вещь. Химические реакции происходят, а конечное состояние соответствует понижением энтропии. Вот это Пригожин. Дальше. Ну вот следующее АБЦ – это модель динамического хаоса. Вот эти люди, вот последний из них получил даже специальную премию Фултса за это дело. Значит, речь идет о том, что динамический эффект на начальных этапах является детерминистическим, в нем записаны просто дифференциальные уравнения, детерминизм, а при некоторых расстояниях от начала вдруг начинает появляться стохастика. И вот это всегда бывает, если уравнения нелинейны и неравновесных условиях. Вот это называется динамический хаос. Дальше. Вот это Пербак, он совершенно гениальный человек, недавно скончавшийся. Значит, он придумал, значит, как описать периодические вещи, которые перебиваются случайными выхлопами. И дал несколько моделей для этого. Дальше будет видно, как это применилось. Дальше, будьте добры. Наконец, четвертый момент АБЦ – это иерархические структуры, что с ними делать, как их анализировать. Вот вы видите три структуры, вот нижняя, средняя и дальнейшая. Значит, что-то с ними происходит под действием радиации на каждой из платформ. Платформы друг с другом связаны, но весь фокус, что они связаны хитро. И на самих платформах происходит самоорганизация, и между ними есть связь. И вот так вот, значит, вот так вот они завязаны, что любые отражения внизу, немедленно они комбинируются в особые элементарные возбуждения, которые стягиваются наверх, и потом те еще дальше. Вот уравнения такие описаны перед вами, они достаточно новые. Здесь есть вещи вероятности, здесь есть детерминистические. Вот эта величина k возле суммы, это важный момент. Это количество элементов в каждом из вот этих платформ. Дальше. Итак, значит, концепция комплексити именно уже в радиационной физике. Как это все применяется? Вот это вся кухня. Значит, если с высоты птичьего полета постараться поглядеть, то мы увидим, что 20 век был таков, что изучали все эффекты, руководствуясь физикой, химией материалов, а именно химическими связями и физическими. Металлы, ковалент, ионные, вандервальс, гидрогенные, то есть водородные связи. Но где-то с начала 21 века увидели, что оказывается при совершенно разных видах связи, оказывается, что но при одинаковых структурах эффекты одинаковые. И тогда удалось выделить 5 типов измененных структур, которые можно было все современное материаловедение разделить. Итак, нано, мы все это знаем, значит, маленькие размеры, фракталиты, особый тип неупорядоченности, содержащий внутри себя порядок. Small dimension, малые размерности, один их двухразмерный. Хиралиты, вот это очень интересно, который сближает с живым. Накручено слева направо ДНК и справа налево накручены белки. Так вот, оказывается, теперь хиральность эти самые ОНТ. Углеродные нанотрубки 100% хиральные, и без хиральности нельзя понять их эффектов. Ну и, наконец, иерархичность. Вот это уже очень обычное дело. Теперь стали мы понимать, глаза открылись, начиная с электронных оболочек, нижних, и потом валентные, а потом уже химической связи, конгломераты и так далее.
Борис, у вас еще 2 минуты.
Готов, все, скажу. Один пример будет достаточен. Итак, на основе этого дела всего, оказывается, можно разделить все эффекты радиационные на 3 парадигмы. То есть распределить их, будьте добры. Дальше. И вот, оказывается, на основе вот этих позиций удалось разобрать какие вещи. Во-первых, оказалось, как вы все, наверное, помните, был вот в этих годах, как написано, авария космическая спутника Фобос-Грунт. Было дело очень трудное понять, но удалось. Дальше. Значит, дальше я сейчас скажу, что вышло, самое главное. Дальше. Вот это вся и математика, все дальше. Математика, дальше. Вот еще дальше. Вот посмотрите, пожалуйста. Химические реакции между дефектами были автокатализ 2В, 3В. Оказывается, выход вот продукции был такой. Значит, ламинарная фаза накопления дефектов, потом вы видите колебания, потом опять ламинарная фаза и так далее. И вот тут есть случайность и детерминизм, и характерные времена, вот они записаны, получается. Вот эта штука, она является базовой для очень многих радиационных эффектов. Дальше. Вот дальше, потому что не успеть. Вот очень важно следующее. Без того, чтобы обсуждать проблемы комплексити, оказывается, можно было сделать, значит, правила, как рассматривать механизмы подпорогового дефектообразования. В книге, скажем, 2 лущиков, отца и сына, эти правила сформулированы. Оказалось, первое правило пришлось подправить, второе было вообще ошибочно, третье – это новое явление, так называемое флип-флоп, когда сингретные химические связи через флип-флоп переворотов превращались в триплет с дальнейшим распадом. Значит, эффект размерностей и очень интересная в разработке пока гетерогенность по атомным массам в твердых телах. Дальше. Конкретные примеры, еще несколько слов. Значит, при изучении скорости перемещения дислокации в зависимости от окачки было обнаружено, что резкий порог, вот это резкий порог, попытались интерпретировать Вахте-Бехтен. Второй человек был Елисеев из Фиана. И, наконец, большая интерпретация была получена с помощью вот этой комплексити. Значит, были получены распределения не пуассоновские, соответствующих характерных позиций, и уже там не получались более точные сравнения с экспериментом. Еще чуть-чуть. И вот последнее. Очень часто, значит, главный механизм деструкции всех ионных кристаллов, особенно касается дела лазерных кристаллов, происходит в том, что получается ионизация и почему-то потом дефект. Значит, анализ таков. Ионизация происходит в глубоких оболочек. После этого эта дырка всплывает в АЖ-каскадах, и позиция отрицательных ионов оказывается нестабильной, и они соскакивают с места. Как только они соскакивают с места, появляется дефект. В окружении играет принципиальную роль. Если оно упорядоченное, одно дело. Если разупорядоченное, то тогда коэффициент усиления 10/4 для сечения дефекта образования. Записано вот так. И вот эта штука, уже совсем последняя, у нас нашло очень интересное применение. Сейчас вы удивитесь. Дальше. Вот, поглядите. Это все было применено в нашей команде международной Узбекистан, Россия, Соединенные Штаты. Мы смогли предложить метод борьбы с коронавирусом, воздействие на его РНК с помощью рентгеновского излучения через АЖ-каскад. Вот и тут всякие детали, это дело признано и опубликовано очень хорошо, и ссылки есть полным-полно в западных Главное следующее, что из-за вот этого множителя назад, еще назад, вот, внимание, вот 10 четвертой, из-за того, что у вас биологические молекулы не обязательно не упорядочены, появляется этот множитель. Из-за этого у вас течение дефектообразования локально становится очень большим. И дефект, и в этом месте РНК вируса повреждается, оставляя живой спокойной ткань, вот это последнее течение, обычная ткань. Вот это было очень важно. И уже совсем последнее, значит, времени нету, друзья. Я хочу сказать еще чуть-чуть. Вот это. Значит, у нас, я не перевел список, более 20 публикаций высокой стоимости, как говорится, с помощью вот этого самого синергетики. Дело новое, нелегкое, даже я бы сказал трудное. Прямо скажем, без профессиональных теоретиков обойтись очень трудно экспериментаторам, которые так хватит у них колоссальное количество забот. Ну вот, значит, вы видите, что было раньше в радиационной физике: подпороги, надпороги. Теперь, что перешли к упорядоченным, неупорядоченным системам большей частью. На это ушло синергетика и началось комплексити. И уже сейчас около 20 публикаций на эту тему. И, наконец, завтра мы предполагаем, что это, конечно, будет комплексити. Для этого нужно что? Для этого нужно в обязательном порядке следующие позиции. Должны быть сложные системы, должна быть неравновесность, должна быть нелинейность. И тогда без идей комплексити обойтись трудно. Самое существенное для лазерщиков, я хочу сказать следующее, что очень тонкий эффект, связанный с когерентностью ваших приборов, замечательнейших приборов, вот его можно анализировать, как он выходит из строя, его когерентность, если обсудить все это дело в рамках теории шумов. А шумами нужным образом описать радиационное воздействие. Вот какая штука. И все, вот, значит, похоже, что по-настоящему скачок радиационной физики будет так. Если у вас будет сочетаться радиационная физика, радиационная биология, радиационная медицина. Если бы им дали время, я бы в равных пропорциях рассказал и про биологию, и про медицину. Так, все, будьте добры.
Все, Борис, спасибо.
Да.
Было
Сейчас,
очень
я хочу
неожиданно.
поблагодарить вас за внимание. Большое спасибо, ребята, коллеги мои дорогие. Ну,
Вам
все.
спасибо,
Если
Борис.
есть
Вот. У нас просто не остается времени на вопросы, к сожалению. Мы вышли далеко за раунд.
Если кому интересно, я всем могу прислать огромное количество наших публикаций. Особенно по вирусу. Это вообще... А нас даже Вашингтон-Пост написал в связи с этим. Ну ладно, все. Спасибо.
Все, спасибо. До свидания.
До свидания. До свидания. Всех благ. Что там?
Thank you for all of us who stay here and for very interesting discussion in our session. And our session now is closed. And next, our session starts in the 1 p.m. Yeah, we start the closing ceremony and winner ceremony, yeah, for a special good poster session. Ребят, нет, не будет каких-то, все? Все, тогда только осталось закрытие.
You are currently the only person in this conference.
So good afternoon. I guess that all of us who was able to come already are here. To tell you frankly, I even surprised that there are so many of us, in spite of yesterday important meeting, which were really enjoyed, all of us yesterday on boats of the trip. Time to conclude our conference is coming. Now, I was asked to make a few remarks. It is more or less traditional for our meeting. So First, I think that most of you will share my opinion that the conference was good from scientific point of view. That we had very many talks, very good talks. Presence of the audience was relatively high. I would say, if to compare with previous conferences, it was better here, even better than we had it in other countries. Many young researchers came. We had excellent poster session. So everything was for the good interest of people to meet each other, to learn new things about our science. And as a new trend, we had a new section this time for optics in quantum technologies. It broadens the scope of our activities. Probably this area will develop rapidly because it is very popular now in all fields. So this is from the scientific and personal points of view. We had opportunity to meet each other, to meet new people, to establish new contacts. So this is first. Second, I definitely have to express our gratitude to the conference organizers, to the program committee, and to the organizing committee, and first of all to the local organizers, Professor Soifer and Professor Pavelyev, who did, and their teams, who did so many for us to enjoy our time here. So I think that you will share. And certainly thanks to all other people who lead sessions, who submitted papers, who did a lot of useful and pleasant things here. This is the second I wanted to mention. So I already told that we had a good poster session, and this year, as usual, during poster session we had a competition for young scientists. The few works were selected, in fact 3 of them were selected by members of the program committee. Then we put this information together, calculated the winners, and so now I will enjoy to announce the winners, and I hope to see them here also. The first winner so we'll do it together. The first winner for young scientists is Alexandra Levshakova from St. Petersburg for the presentation Laser-Assisted Synthesis of Electrode Materials. The winners receive award of 2 first awards, 20,000 rubles, and the third award 10,000. So the second one is Boris Lisich. He is from Federal University of Yekaterinburg, from Urals, for the work bulk damage domain growth created by femtosecond laser in magnesium doped lithium niobide. Is he here with us? Sure, yes, certainly. Shulki, yes. And the last one is Danila Imirenkov from Lomonosov State University. The effect of the gasotransmitter natrium NO on the parameters of platelet aggregation and so on. Long name, but good, excellent. My congratulations. So, are there any questions concerning this meeting? Maybe some remarks, some proposals, somebody is not satisfied with something. For example, still we have some cancellations of presentation. Not so many, but fortunately not too many of them. Well, this year it was much better than before. But still there are some, which is not good. So we have to be more careful about this. There were some problems with the program. Not everything was clear from the leaflet of the program. Maybe something else. Yes, just a few minutes ago, some of my colleagues proposed that next year probably it will be necessary to have a Young Scientist Award not only among poster presentations, but also for oral presentations. Before, we tried to do this, but it didn't work because there are very few young people who presented oral talks. This year it is definitely different, so probably for the next year we should divide. But this competition should be different. For posters is one, for oral presentation is another, maybe with different ranks and money. Questions, proposals? No? If not, then as usual, we have to speak about the future. And so now we have to announce what will be. Our next conference is already fixed. We discussed this, made a final decision during a program committee meeting here. And the next meeting will be held in Vladivostok next September. It is about the same period, something like third week of September, because at the beginning of September there is a world meeting in Vladivostok, so we should avoid this time. So it is far away, certainly, Vladivostok, but people say that at least nowadays the price of plane tickets is about 25,000, forth and back. Return ticket, it's quite, at least before people could go abroad easily. Maybe the organizer of this meeting will be the Institute of Automation and Control Processes of Far Eastern branch of Academy of Sciences, very well-known institute with a very good team, with a team of about 200 researchers working in the field of optics, photonics, and so on, so very close to what we are doing. And the leader of this team and the co-chair of this meeting will be academician Kulchin, very famous scientist and vice president of Russian Academy of Sciences and president of the Far Eastern branch of Academy of Sciences. So I hope that we'll have a comfortable conditions for our conference, and it will take place in the building of the Academy of Sciences in Vladivostok, just in the center of the city. It's not on the island, it's in the center of the old city. So what is next for the future? We discussed major problem is to what extent we are international and to what extent we are national. This year we have a big progress in this. We had quite many, not many, but more than 10 participants from outside Russia. We had many online presentations from abroad. So if to compare with the previous 2 meetings, it is a great progress in this direction. We'll try to work further. How it will be successful, we'll see. What will be the international situation. But already we discussed at the meeting of the program committee one interesting possibility which was proposed by Professor Paveliyev from here. And he has very good contacts, scientific contacts with India. And probably we'll try to organize a meeting in the year 25, not next year. Next year is fixed, it is in Vladivostok. But in the year 25, maybe we'll try to do it in India, maybe in some other place, we'll see. And also we hope that in Vladivostok, which is very close to China, we'll have many Chinese participants. We'll see. So, any questions concerning next meeting? If not, then thank you all again. I really enjoy our meeting, seeing you, talking to you, listening to your excellent talks, presentations, and see you again next year and in many other places when it is possible, so that we organize a team working in the research field in Russia. So goodbye, good trip. No drinks.